Good afternoon and welcome to Catalan Cymru revision sessions. This session will focus on A2 chemistry and will be presented by Mr. Peter Black from Penglai School. Now the session will last around 45 minutes when Mr. Black will go through the relevant subject content with you. But if you do have any questions, please use the question and answer section and I will do my best to answer your questions during the session itself. Now the session will be recorded and the recording and any relevant resources will then be uploaded to the e-sgol website in the Catalan Cymru area.
Okay, good evening or good afternoon. Welcome to the last session we'll be doing with Catalan Cymru. And we're going to look at the obviously topic of kinetics, which has massive links to year 12. You've done a lot of kinetics in year 12. Mainly looking at the techniques you use to study rate, but also, the Boltzmann distribution curves, so the effect of catalyst, the effect of temperature. So definitely, make sure you're aware of those aspects from the year 12 course. I have put a link later on in the PowerPoint that goes back to a previous Cymru session area on this. So it's for year 12, but definitely worth looking at if you're in year 13. So, typical graph, we monitor the rate of a reaction over time, and you can see here typical things that would expect to happen during a reaction. You'd expect to see product forming and you'd expect to see the concentration of reactants decreasing over time. And we can get quite a lot of information from these kind of rate time graphs or concentration time graphs. So we'll certainly be looking at some of these in a moment. But before we do that, let's just very, very quickly, like I say, go back to year 12 if you're not at all confident on these. There's different techniques we use to monitor rate. Obviously, this is a reaction which would, that's right, generate gas. So we'd expect here to see the gas syringe moving outwards. We could record the volume every minute or every 10 seconds, whatever you think is relevant for that reaction. And here we're monitoring the change in mass, and I hope you know
Excuse me, Mr. Black. I thought it was an issue with my computer, but it appears they can't hear you. We still can't hear anything. You can see the PowerPoint, but nothing, can't hear anything. Thanks for your patience. If you're listening in, I'm hoping that Mr. Black will be back soon, and so hopefully we can resolve the issue. I still can't hear you, Mr. Black, so I'm not sure what the issue is. I'm in the chat. We still can't hear you. So I don't think anybody else, if somebody can, of the attendees can hear him and it's simply me, then please let me know. But I think there's a technical issue your side, Mr. Black. Obviously, the hope is that we'll get this resolved quickly, but we will still give you the designated time. So the session will still be 45 minutes, even if we have to continue over that time. And if that takes you into another session, I can only apologise. That might mean that you'll have to look at the end through the recording. you like to see whether leaving the meeting and coming back into it will help or not, Mr. Black? For those attendees, thanks for your patience. We'll see whether this will work now.
Can you hear me?
We can hear you, Mr. Black. It might be beneficial not to do the camera and solely do the PowerPoint, if that is possible, because that tends to ease the issues.
That's not to what, sorry?
If you don't have the camera on, it often helps with the
okay. Yeah.
Maybe just see the PowerPoint.
The problem is I will need to finish at 5 o'clock this evening. So I'm wondering if we need to reschedule to another day or should I carry on?
I don't know what the procedure is with such an eventuality.
Okay. I think, how would you feel about doing tomorrow? Can't.
I can try. I can certainly try.
Well, I'll tell you what, shall I see how long it takes me to get through and then I can pick up the rest tomorrow if need be, so they get the 45? Yeah,
let's see how we get on.
Okay, bear me a second then. There are things I can, well, I won't put camera on. I'm just going to share my content. Well, we've done quite well for 4 weeks.
Yeah.
You know, these things happen. Right, share. I think that's the one I want to share. Slideshow. So did you hear me from the start or did it not work from the start?
We heard you briefly at the beginning and then we lost you.
Okay.
Right. Excellent.
Super quick. I'm flying through this bit because it's very basic. Okay. So colorimetry. We've got a color change and don't worry too much about this. I'm just saying, you know, if we were to monitor this reaction, ligand exchange, you can see that this complex we start off with would be absorbing light at 520 nanometers. So if we wanted to monitor the rate, we could look at what happens to the absorbance at light at 520 nanometers, and we'd see the absorbance dropping on our colorimeter. Or we could look at the wavelength of about 690 nanometers, and as this substance forms, we'd actually see the absorbance increasing. All right, so you know, just a little idea about how colorimetry works. Then we've got this reaction here, and as I said, it forms a precipitate, and this causes the reaction to become opaque, so you can't see the cross. And this is what we call a clock method. There's lots of different clock methods. A clock method is a timed event. So, for example, here we're timing how long it takes for the cross to disappear. It could be we time how long it takes for, I don't know, collect a certain volume of gas. You know, how long it takes to collect a certain mass of gas. You know, you're timing an event. How long it takes for something to dissolve, whatever. And it's important you know that in a clock method, your rate is worked out with 1 over time, and that gives you the unit. S to the -1 for rate. Okay, so the clock methods, they're a different way of working out rates, 1 over time. Don't forget that is year 12, but I have seen on year 13 papers, and my year 13s not know how to work out the rate. So 1 over time for a clock event. Hopefully you know this reaction as well. This is the iodine clock method. You'll see that you're producing iodine, so you've got some starch in this reaction mixture, and you time how long it takes that blue colour to appear. Right, just a little by the side. We usually put some fire in there as well, and just to let you know why, starch goes blue-black with even a very, very small amount of iodine produced. So we kind of put the fire in there to give us a bit, make the reaction last a bit longer before that blue colour appears. So that's the iodine clock method, and here, you know, just showing you how you could monitor the rate here. Basically what you're doing is you're changing the concentration of the potassium iodide. You can see the starch sulfuric acid and the starch and the thiosulfate staying the same. But what you are changing is the concentration of the iodide. And the way you're doing that is you're adding water to the reaction mixture. Okay. One of the things that I would point out to you is that the reason we add different amounts of water so that we always have the same volume overall. We've got a constant volume. Each of these volumes add up to 56 centimetre cubed. And the reason we do that is then a change in the volume of the iodide is proportional to the change in its concentration. So in effect, if we go from 10 to 20, we have doubled the concentration of the iodide. But you'll notice here they've used less water. So that gives you the constant volume means that change in volume is proportional to change in concentration. Okay, and this is the kind of graph you would get. You can see here, as you'd expect, increase the concentration of the potassium iodide, we're increasing our rate of reaction. The amount of time taken, by the way, would actually be less with a higher concentration, but that would result in a faster rate one at a time. How do you monitor this rate then? Well, there's no gas, there's no colour change. So this is a technique you don't really need to know much about year 13 this year. You would have to do titrations on it. And you'd have to do this technique called sampling quenching, but that's off your syllabus. But you'd have to take samples and you could titrate the hydroxide ions to see how many of those are remaining as you proceed through time. So once you've got your data, you've got your time on your horizontal axis. Here we're measuring how much gas is being given off every minute. If we wanted to find the rate, we take what's called a gradient. And hope you know how to take a gradient. I'll just remind you. So you take your gradient at any point on that curve, at any time, you draw a tangent, and then you do y over x. And that's going to be very, very important to us in a moment. Okay. Initial rate, hopefully you know that means you're going to take the steepest part of the curve. And as I said, I have done, which allows me to kind of skip through this stuff quite fast. I have done a video here previously in year 12, and if you click on this link, it takes you to that presentation. You'll also find the PowerPoint on the Carl and Cymru area. So let's bring us into year 13 then. In year 13, these are things that we need to know. Again, you can see here the principles underlying the measurement of rate of reaction. So that's really important, but not the sampling and quenching. So we can kind of, get rid of that in a way. Okay, so once we've monitored a rate of reaction, why are we monitoring rate of reaction? Well, it's so we can write this. It's called a rate equation or a rate law. And we're just going to go through very quickly the components of this rate law. So we've got our rate is equal to what's called the rate constant multiplied by the concentrations of the reactants. It says compounds or molecules here, but it's the reactant compounds or molecules. And then we've got these indices values next to them, X and Y. And these are called the orders of the reactants. Now, I hate equations like this, A and B, not A and B. What I've got here then are some reactions. And you can see here next to them, we have the rate law written down. And there's something I want to point out to you about the rate laws, these indice values, these orders of the reactants. They are not reflective of the stoichiometry. Now, it just so happens on our first rate law, you can see the NO, the nitrous oxide, has been raised to the power of 2. And there's a 2 in front picture. You might think, oh, okay. And the O2 has just been raised by 1. And you might think, well, that does reflect stoichiometry, but look at the others, okay? So if I pick out 2 particular, you can see there our rate law does not reflect the stoichiometry in any way at all, all right? It does for that one, okay? But it doesn't for this one. Look, you see there's a 2 ICL and it's not raised by an indice of 2. And what I'll be showing you later is that we have to derive these orders experimentally. And we'll look at some techniques we can use for doing that. Okay, if we look at most of your rate laws here, they don't show this, they show that the stoichiometry is not reflective of the order. The order has to be found experimentally. So we'll look at that. So first of all, why is order important? Well, let's look at an example. Let's look at this rate then. So we've got a rate law here for this reaction of nitrous oxide and chlorine, which I think was one of our ones there. No, it wasn't. Okay. So what does order tell us? Well, they tell us how a change in concentration of that reactant affects the rate. And hopefully you know that 0 order means that that reactant has no effect on the rate. So it doesn't matter what you do to its concentration, the rate will stay at its constant value. Which is kind of weird because you're always told to increase concentration, increase rate, not if you're 0 order. First order, rate's proportional to the concentration of the reactant. And what that means is that if you double the amount of that reactant, your rate's also going to double. And that's going to be really important for us in a moment. And likewise with second order, what we say here is rate of reaction is proportional to the square of the concentration of the reactant. Well, that means that if you double the concentration of these kind of second order reactants, the rate will be 2 to the power of 2 times faster, i.e. 4 times faster. If you triple their concentration, then the rate will actually be 9 times faster. 3 to the power of 2 is 9. So they're obviously very, very important. And I just thought we'd have a bit of fun here. I've just given you silly little values, really. And, you know, if we were to work out the rate then of this reaction, we take our rate constant that I've given a silly value of 2, and we've got our concentrations here. So if we look at the rates, okay, so this is how we work out the rate. The 2 is the rate constant, see the same for both of them. And then we've got the concentration of the NO, which is 2, but I've raised it to the power of 2 because of the order. And then the chlorine is 2. All right, so I haven't changed there. You can see where those values come from. And you can see the effect of doubling the concentration of the NO. So the Cl2 stayed the same, but the NO has been doubled. And look at the effect on the rate. How many times faster is that rate? Okay. Well, you've got to work out how much faster a rate's going. Obviously, you take your faster rate, you divide it by a smaller rate, and you'll see now 64 divided by 16, the rate's 4 times faster. And that's only because we've doubled the NO concentration. Okay. So doubling it has made the rate 4 times faster. That tells us that the NO must be second order. Let's look at the chlorine. Well, if we look at the chlorine here, what I could do here, my NO stayed the same, and I've doubled my concentration of the chlorine. Let's work out our rate. So our rate is 2 times 4, squared, and then we've got the 4 here as well. And you see our rate is now 128, and that's again twice as fast. So you can see here the NO's been kept the same, so that's good. That's not going to affect our rate. We've doubled our chlorine, the rate's doubled, and that tells us that the chlorine must be first order. So you can see the impacts of the indice value, especially when you second order. You double something, it will go 4 times faster. Triple it, 9 times faster. So let's look at a question, and this is off an exam paper. It tells you the order of the NO and the chlorine. So if we were to write that as a rate equation, we've got rate equals a rate constant times the NO raised to the power of 2 and the chlorine raised to the power of 1. Okay. And, you know, a really simple question might be, well, they might give you some concentrations and ask you to calculate the rate. And they have to give you the rate constant as well. So all you need to do is what I call plug and play. So you can see the concentrations are both at 0.11. So if we plug that into our calculator, we've got our rate constant times by the NO, which is 0.11 squared, and the concentration is chlorine, which is just 0.11. And that gives us rate equals 1.21 times 10 to the minus 7. Just one thing though, I don't like about that answer. And I hope you also know what I don't like about the answer is your units. And your units of rate here, because it's changing concentration over time, would be mole dm to the minus 3, s to the minus 1. Okay, so changing concentration over time. Okay, so we're going to talk then now about, we know what order means and the impact it has on the rate of reaction. We're going to look at the 2 ways we can establish the order of a reactant. Okay, so there's 2 ways, like I say, you can look at changing concentration of a reactant over time, or the second method is what's called using the initial rate data. So let's, I'm just reiterating, as we said earlier, order is not established from the Banach equation. Just like the rate constant, which we'll look at later, it's got to be found experimentally. So what we're going to do then, we'll look at the first method, which is where we look at changing concentration over time. And to do this, you've got to be able to take gradients and work out rates. So I'm just going to flick through this one very quickly, and you can look at this PowerPoint yourself in a moment. We're going to look at a specific question from the exam. So this is, we're looking at a reaction here of hydroxide ions with bromoethane. Hopefully you know this is what we call nucleophilic substitution or hydrolysis. And what we're going to do is we're going to try and find the order of the bromoethane. So if we want to find the order of bromoethane, what we'd have to do is we'd have to look at how the concentration of the bromoethane changes over the course of this reaction. Okay, so we'd plot a graph like this. One little thing that I would tell you as well is that if you want to find the order of bromoethane, the other reactant must be in a massive, massive excess. So usually about a factor of 10 in excess. And the reason for that is as this reaction proceeds, both reactants concentrations will decrease. But if you've got a massive excess of the hydroxide ions, the decrease in its, the amount of hydroxide ion compared to how much you started with is minimal. Whereas this, as you use it up, the concentration is going to be going down. So the other reagent, if you want to find the order of one reactant, have the other one in a massive excess. So you can see here then we've got a graph, typical kind of rate graph. You can see as the concentration of the bromomethane decreases, we can see our rate's decreasing because we've got a curve. And what we could do is we could actually use this curve to work out the order. So what I've done here is I've taken my initial rate, right? So I've taken the steepest portion of that curve, and I'm going to take my gradients, which we discussed earlier, which is y over x. And you can see my initial rate is coming out as 1.6 times 10 to the minus 7. Just showing you, and you can see there, if I just show you where I've got that from, my change in y I've taken as being 2, and it took, I think I worked it out as 80, how long is that? That's 12 seconds, took 12 seconds. Okay, however, notice what I've done here as well. Now be careful with the examiners, they love doing things like this. Initially you'd think it's 12 seconds, but it's 12 times 10 to the 3 seconds. So if you're working out your initial rate, you couldn't divide by 12, you'd have to divide by 12 times 10 to the 3. So that's my delta y over my delta x. 2 times 10 to the minus 3. Look at the put times 10 to the minus 3 there, divided by 12 times 10 to the 3, and it gives me this rate. And now what I'm going to do is look at my rate at another concentration. And I specifically chose my rate at a concentration of 1 mole per deciliter cubed, and there's a good reason for that. It's half the concentration of my other rate. And so what I'm going to do now is work out my rate again. So you can see, taking my gradients, I've gone from 1.7 times 10 to the minus 3. So I'm going down to 0, and that took 20 times 10 to the 3 seconds. So that works out my rate there. So just recapping, I've worked out my rate for my gradients from the initial rate where the concentration was 2, and I'm looking at my rate when it's half that value, the concentration is half that value. And what I do then is I compare my two rates. Okay. Hopefully you know from earlier, that's where you take your faster rate and divide it by a smaller rate. And that gives me where my rate is. I can see at the half, when I double the concentration, my rate's going twice, well, almost twice as fast. So that tells me I must be first order. Okay, my bromoethane has to be first order. If you double the concentration, your rate doubles. So that's one way of doing it. Okay. If you've got a graph like this, so this is another reaction. You can see they're monitoring the change in the ethanol. If you look on this graph with time, you can see that despite the concentration of the ethanol going down, what's happening to your rate? Well, nothing's happening to your rate. So your concentration of ethanol is dropping. It's a reactant. All reactants drop over time, and yet your rate's proceeding at this constant rate. And what that means then, what does that mean? Well, that means our ethanol must be 0 order. Even though the concentration drops, the rate is unaffected. And then finally, a second order graph. Well, really second order graph, you can spot them straight off because they're really, really steep at the start, and then they tail off very, very quickly. So you have this massive decrease in the rate. And that's because, remember, they have a bigger impact on rate. Okay. Now there's a much, much easier method for establishing order. I did say, you can take gradients, and sometimes you have to because the exam question stipulates work out the gradient and then work out the other gradient at a suitable point. However, if they don't stipulate to use gradients, I would use half-life. So what's a half-life? Well, half-life is the time it takes your concentration to halve. So that's what I'm going to show you now how to do, and then how you use those half-lives. So what I've done then is I'm going to take my first half-life. I'm going to start you don't have to start at 2, but it's an obvious place to start. So pick somewhere obvious to start. You don't have to start at 0 seconds. You can start anywhere on this graph you like for your first half-life, but it's easy to start from 0. Okay, so I'm going to see how it takes to drop by half. So it takes to get to 1 mole per decimeter cubed. And we can see here, be careful with your axis, you know, you can see here each square is worth 0.5. So I worked that out as taking 8.5 seconds for my first half-life. It's not 8.5 seconds. The examiners, they're tricky. It's 8.5 times 10 to the 3 seconds. Watch those axes, look for these, you know, little points. My second half-life then. So if I take my second half-life, so obviously I'm going to look at my the time it takes to drop to 0.5. Okay, that's obviously going to be when my second half-life is. And it's the step, right? So going from that time to that time. Okay, so don't include from 0 because we've already, that's our first half-life. So it's from going from 1 to 0.5. And if you look again, you'll see that you get the same half-life. And this is typical of a first order reactant. So your first order reactants, they have a constant half-life. Just going back and reminding you, you won't need to do it for if it's 0 order because it's just constant gradient. If it curves, take a half-life. First order, it will be a constant half-life. And your second order, because of that kind of steepness to the curve, what we start finding with the second order reactants is your half-life increases each subsequent half-life. And you see it massively increased by your third half-life. So half-lives is the much better way to go. So I'm going to talk to you now about the other method we can use to determine order. It's a different method. It's called initial rate data. And this is, like, how you'd establish order with the Idean clock method. That's an initial rate data method. So we've got some information here. We've got some rates of reaction, and they're done at different concentrations. Okay, so we've got this reaction between nitrogen dioxide and carbon monoxide, and we're being asked to work out the order of the 2 reactants. And what I do, and you've got to have your own way of doing things. You have to use logic here. The thing I usually look at to start with is, well, what's happening to the rate? And I just look at what's happening to the rate. Remember, you take your faster rate and divide it by the slower rate. And one of the first things that sticks out to me is this here. If I go from here to here, I can see that my rate's doubled. And if I look at what I've done going from there, well, I've done nothing to the nitrogen dioxide, but I have doubled my carbon monoxide. So my rate's doubled, I've doubled my carbon monoxide. That must be my carbon monoxide, must be first order. And I can see similar here. Look, if you look here, between this run and this run, you can see again my rate's doubled. What have I done? Well, I've done nothing to the carbon monoxide, but I have doubled my nitrogen dioxide, and my rate's doubled. So that means both those things must be first order. Okay? So it's just using initial rate data. And like I say, I usually look at what happens to the initial rate because it usually gives you a good idea what's going on. If I was to write to my rate equation then for this reaction, there we go, there's my rate equation. By the way, if something's 0 order, it probably won't be included in the rate equation. It just won't be there if it's 0 order. Now, I'm going to talk to you about calculating the value of the rate constant in a moment. The answer is there for you. So when you want to go back to the PowerPoint, you can have a look. And we're also going to look at the mechanisms later. So these questions we'll come back to on the PowerPoint for yourself. This one's a bit trickier, but again, it's all about using logic. Again, I'm going to use my initial rate data. And one of the things that I first of all notice is initially it looks like there's been no change in rate here. 1.4 times 10 to minus 2, but there has. Look, 1.4 times 10 to minus 3. This rate is actually 10 times slower. How can it be 10 times slower? Well, what's the data they've given us? They've given us pH. And this is quite common. The examiners like to kind of tie in to other sections of the course. So you should know, going from pH 0 to pH 1, your pH, first of all, is your H plus concentration. So obviously there's H plus ions being looked at here. And you should know, going from 0 to 1, your H plus concentration is decreased by a factor of 10. All right, a factor of 10. And if you look here, you can see also we've decreased our concentration. Our rate's decreased by a factor of 10. So already I know something about the H plus ions. But there's something easier to spot. If I look here, can you see my rate's doubled? We've gone from 1.4 to 2.8. Let's see what's happened here. Well, we've done nothing to the Fe3+, we've done nothing to the H+ concentration, but we can see we've doubled the SN2+, and my rate's doubled. Okay, so that's something to look for, you know, what's happened to your rate. And because the SN2+ has doubled and the rate's doubled, that must mean the SN2+ is first order. Right, let's look at the other species. Okay, like I say, this is the this is going to help me with my H+. Okay, so pH is, like we said, it's a H+ concentration. If you look at the ones I've lined here, we can see the rate's gone 10 times slower when we've gone from pH 0 to pH 1. Or you could say going from 1 to pH 0, it's 10 times faster. Depends how you want to look at it. But ultimately, what that means is that if my H+ concentration is changed by a factor of 10 and the rate's changed by a factor of 10, the H+ must be first order. Okay, so what about the Fe3+? Well, if you look at this one where we've changed the pH, we've also changed the H+, but there's been no effect on the rate. Okay, because in effect we've also doubled here the H+, and that should, in theory, actually make our rate, you know, not as it would affect the rate. It wouldn't be 10 times slower. It would actually only be 5 times slower, because this would be doubling our rate, and this would be making our rate 10 times slower. So it would only have an effect of making it 5 times slower. But we can see here that the Fe3+ has no effect on the rate. It's coming out as 0 order. Okay, so if we throw out our rate equation, it's only SN2+ and H+ included. And there's something I want to point out to you about the H+. It's not a reactant. Why are we even looking at it? Well, it's affecting rate. So something that affects rate, but as in actually a reactant, it's got to be a catalyst. And that's quite a key thing there. If you ever come across something that's affecting rate, but is it in the actual equation itself, it must be a catalyst. Okay. So, little video there, you know, you need to practice those. They are very, very tricky. Some of them are straightforward. Some of them, like that one there, are tricky, and you may need to go back through that little PowerPoint yourselves to get the idea how you work out your initial rates, sorry, your orders. Oh, you can click on this as well. It's quite a good video on YouTube. So just very quickly now, I'm going to go through order and mechanism, why orders are so important. Well, again, you know, you should recognise this as being hydrolysis or nucleophilic substitution. And this is a very, very basic outline of the mechanism. Now, actually, if we look at the mechanism using rates, we can actually suggest that there's another way of looking at that mechanism. It's a bit more complicated. And you can see here that we say that that reaction actually occurs in 2 steps, not 1 step. And the first step involves the hydroxide ion attacking this carbon and forming this intermediate where you've got 5 bonds around the carbon. Now, that's going to be difficult. And this is called the slow step here, but there's a better term the exam board use. They call it the rate determining step, or RDS. And I'm going to ask you a question here. Would increase the amount of hydroxide ion affect our rate? Well, hopefully you're going to say yes, because it's going to increase the chance of a collision in this slow step, so it could speed that slow step up. And the same with the bromorethane. If we increase the amount of bromorethane, would that affect the rate? Well, yes, because we've got more of it, we're going to increase the number of collisions. So this step would speed up. So both these things affect rate. Okay, if we go back, are those molecules in or before the rate determining step? Yes, they are. They're both before the rate determining step. So I'd expect to see them have an order. Okay. So first, one molecule is in the RDS, yes. So both of these should have orders, and both of them should appear in the rate equation. So that should be our rate equation there. Now, let's look at this reaction. There's another way of looking at that reaction. Okay, so same reaction, it's still hydrolysis, slightly different molecule. And what they're proposing is this has been our RDS, so slightly different mechanism. And they say, well, what happens is the bromide ion, bromine, comes off first of all, and it creates this carbocation, and then the hydroxide comes in after that. So if we look at our RDS, and we think about what we said about RDS, okay, so these important steps here, if your molecule's got an order, it comes before the RDS. If it comes after, it would be 0 order. And if we look at this mechanism then, What I'm going to suggest to you is that that doesn't work anymore. Well, why not? Well, the hydroxide ions come in after the RDS. It shouldn't be there, all right? If it comes after the RDS, it's zero order. And actually, if we look at the rate equation, we see that that's the case. Think about it. This is our slow step. If I increase how much hydroxide ions I've got, would that make this step go faster? Not at all, okay? So that's your mechanisms. It's worth knowing those mechanisms for the exam, just because of their connection to rates reaction. Sometimes they actually ask you to propose a mechanism, and that's called an SM1, and that's the SM2 type, okay? And you can see there's your rate. You can see the hydroxide ion is involved in that slow step there, so we've included it in our rate equation. Quite often get asked what a rate determined step is, and I'll just put that answer there for you. It's the slowest step in the reaction mechanism. Okay. And now we're going to just very quickly look at finding what's called the rate constant. So just like order, you can't find a rate constant from any other method other than looking at experimental data. You can use what's called the Arrhenius equation, which we'll come on to later. Very challenging bit of maths there. But we can, the easiest way to find a rate constant is by looking at some initial rate data. And all you do is you first of all write your rate equation. So you'd need to know what the rate equation was. In this case, we've got both the, this is from our previous question, by the way, we've got the tin and H plus ions as being first order. Okay, then what we do is we rearrange our expression to find K. All right. So I can see that all I've done is rearranged it. I've moved these across. Here we're multiplying, so on this side we're going to divide. And in case you need to, you'd have to work out your H plus. This links back into your topic 3.9. You just do shift log of the pH, minus pH. So I think shift log of minus 0 is 1. And now you can see you've got your rate constant. Okay, so you just pick any line you want in particular, absolutely any line you want. I've chosen, which one have I chosen? I've chosen this line here. Okay, obviously the tin's not in there because it's zero order, but you can see I've got the SM2 plus as 0.2. I've got my pH as 0, and I've got my rate as 2.8 times 10 to minus 2. Unit, really important, you can work out units. So when you work out units, you kind of need to think about the units of rate R. So rate is mole dm to minus 3 s to minus 1. And then our units of concentration, well, that's the SN2 plus, mole dm to minus 3. That's our H plus, mole dm to minus 3 as well. They cancel out. Okay, and then when we rearrange our units, we bring that up to the top. So we take the reciprocal of this, mole to the minus 1, dm to the 3, and we leave s to the minus 1 on the top there. So that's how you find your rate constant. You can pick any line, try it yourself. Maybe pick this line here, work out your H plus concentration by doing shift log minus pH, and then plug your values in using your rate equation after you've rearranged it, and you should come out with 0.14 again. You can pick any line you like. So last of all, the Arrhenius equation. This is the Arrhenius equation here. You have to know it for the exam, and you also need to know when you're using this where you're to convert your activation energy. You'll give it in kilojoules, double guarantee it. You just need to convert that to joules by times into by 1000. You also need to know where your exponential button is, which is this button here. Okay, so you'll have to find where yours is on your calculator. And then you just plug your values in. And like I say, they'll give you these values. This is called the collision factor. This is the activation energy. This is the gas constant, 8.31. And they'll give you the temperature. That has to be in kelvins. If you want to find the collision factor, so you find in K, you just use that. If you want to find your collision factor, really simple rearrangement. Instead of multiplying the collision factor by the exponential of this, you just rearrange it. And you divide your rate constant by the exponential of the activation energy, okay, and the RT. If you want to find, that's your collision factor, sorry, I have to repeat it there. If you want to find your activation energy, it involves quite a lot of rearrangement. The first thing we have to do is we have to get rid of the exponential. So we take natural logs of both sides. You can see that's got rid of the exponential. And then we just rearrange. But you need to practice the rearrangements. So I've just taken EA over this side, minus EA, it becomes plus EA. And then I take my natural log on that side, because that side I'm adding, so on this side I'll be subtracting it, okay? And then finally, to get rid of the RT, we're just going to multiply by RT. And then the final one is where we take natural logs again. This is, there you go, bear me a second. Okay. This is actually not finding the activation energy, this is for finding temperature. Let me go through, I've done the same thing, I've got rid of the exponential, I've taken the natural log across, I've got temperature by itself now. The next thing I need to do is just take reciprocals to get RT on top. Okay, so hopefully you can see how I've done that. And then finally, what I'm going to do is just rearrange to get T by itself. Okay, so I'm multiplying by R there, so now I'm going to divide by R. So in effect, those are the rearrangements of the Arrhenius equation. I'm sorry I had to fly through that. I'm sorry about the technical issues. The PowerPoint is there. Hopefully you can work your way through it. I'm a little bit late, but I think I've done what I can do.